Hello everyone, my name is Song Chu Ming, and today I will present about BEKG2443 Engineering Maths 2 assignment. Our group is Group O, and my group member is Na Yit Ying, Teo Boon Kai, Tan Xin Yi, and Song Chu Ming. The importance of Green's theorem is one of the four fundamental theorems of calculus. The gradient theorem for right integrals are Green's theorem, Stokes' theorem, and the divergence theorem. It also defines the relationship between the macroscopic circulation of curve C and the sum of the macroscopic circulation that is inside the curve C. In Green's theorem, we use the convention that the positive orientation of a simple closed curve C is the single counterclockwise traversal of C. At the left side of the figure, we can see that positive orientation, and it is counterclockwise. And at the right side of the figure, we can see that it is negative orientation, which is clockwise. Terminology. Before we go through Green's theorem, we need to understand what is meant by simple closed curve. And there are four examples of curve at this figure. First, it is a simple but not closed curve. And the second figure is a simple and closed curve. And the third one is closed but not a simple curve. And the fourth one is not closed and not simple curve. And at the left side of the figure, we can see that it is a simply connected curve. And at the right side, it is a simply connected, but at the center of the curve, there is a hole. And Green's theorem is applied to the simple connected and without holes curve. And simply connected means the region is closed, simple, and without holes. Green's theorem. Let C be a positively oriented, piecewise smooth, simple closed curve in the plane, and let D be the region bounded by C. If P and Q have continuous first-order partial derivative on an open region that contains D, then the equation will be first integrals area bounded by C, P dx plus Q dy is equal to double integral area bounded region by D, del Q over del x minus del P over del y, del dA, which is equals to double integral area bounded by region D, differentiate Q with respect to x minus differentiate P with respect to y, dA. As long as the curve is closed, we can use a double integral to evaluate a line integral.
Now let's see the example. Example 1. Use Green theorem to evaluate the equations where C is shown below. This one is f x y and then g x y. C is a triangle with a positive orientations. This is a graph that we draw using GeoGebra. First of all, we need to find these three lines. By using the general equation of the line, y equals to ms plus c, we can find that this line is equal to y equals to negative x. By converting the subjects from y to x, it will become x equals to minus y. Here will be x equals to 2y. These three equations is needed for the integration later. Now let's see the calculation part. First of all, we need to differentiate these two equations that I mentioned just now. This one and this one. fxy with respect to y, gxy with respect to x. Next, by using the Green theorems, substitute fy and gx inside the theorems. Integrate in terms of x, then y. These two values is come from the equation that we found just now. X equals to minus y. X equals to 2y. X equals to 2y. X equals to minus y. Here, minus here. Then, these two values, 3 and 0, is come from the line y equals to 3 and then y equals to 0. So, we can find that this area. Okay. Then, just do normal integrations. In terms of x, subs 2y into the x, minus y into the y, minus. Then, integrate in terms of y. Just sub 3 and then minus with the 0. So the final answer will be 135.
So now I will keep going with the example 2, which is evaluate the line integral, which is the line integral of the C region, which y square dx plus 3xy dy. If the boundary is the semi-annular region D in the upper half plane between the circles, which is have the equation of x squared plus y squared equals to 1 and x squared plus y squared equals to 4 shown below. So this is the diagram given. So when we got this kind of question, the first thing we need to do is plot the graph. So we also use the GeoGebra apps to plot our graph. So this red line, the bigger circle, is represented by the equation, which is x squared plus y squared equals to 4. It has a radius of 2 and has the theta of pi. And the smaller circle, which is represented by the equation x squared plus y squared equals to 1, and it has radius of 1 and the theta of pi. Okay, so now we will continue with the calculation part. From the green theorem, we just learned that this equation can be transformed into another form. So we assume that this y square with the dx, this y square is the fxy and 3xy is the gxy. So we know that it can be transformed into the gx minus fy. So when the fxy is y square, so we can know that the del f del y is 2y. And we also can know that the del g del x, which is the derivative of g in terms of x, is 3y. So we can get that this equation. When we get this equation, we can substitute the y into r sine theta, and we substitute the dA into r dr d theta. So after that, we integrate this r sine theta in the terms of r, so that we get this the 7/3 sine theta, and we also integrate it into this. So we also know that the limit of the boundary of R is 2 and the lower circle is 1, the small circle, and is from the pi into 0 as the graph thing like this. This is the 2, this is the 1, R2, R1, and this is the pi to the 0. So that we can get the final answer is 14/3.
Using the green theorem to evaluate the equation where the C is shown below. So this is the diagram given by the question, and then we draw the diagram using the GeoGebra so that we know the upper boundary for y is 2 negative x squared and the lower boundary for y is x squared negative 3. The upper boundary for x is 1 and the lower boundary for x is negative 1. Then we continue to the calculation part. The fxy is the dx part, so fxy is equal to y squared negative 6y. Then fy will be 2y negative 6, and the gxy part is the dy part. So gxy will equal to y power of 3 plus 10y squared. So gx will be 0 because the gxy have no x inside the equation. Then we continue to the integration part. So integration, we put all the boundary inside the double integral. Then we integrate dx first, then we integrate y first, then we integrate x. And inside here we can see the 0 negative 2y negative 6. This is the gx is the 0 is the gx and the 2y negative 6 is the fy. This is from the equation gx negative xy. Then we get the negative 2y plus 6, and we integrate it by y. We will get the 35 minus 14 x squared, and we integrate it by x. We will get the answer 182/3. So this is the answer for the example 3.